So you train a frontier model on a massive, web-scale data set. And that data set is just a chaotic, contradictory
Oh,
mess.
absolutely. It's full of noise.
Right. For every mathematically rigorous proof or factually accurate Wikipedia article, there are just dozens of forums, blogs, scraped sites asserting the exact opposite.
Yeah, the internet is not exactly a curated source of truth.
Exactly. Yet somehow gradient descent navigates this contradictory landscape, right? And the resulting model emerges with a distinct preference for the correct answer.
Which is something we've kind of historically treated as this comforting, almost magical property of scale.
It really is. But it forces a fundamental question regarding the architecture itself. Does the objective of next token prediction actually possess like an inherent compass for the truth?
And that's a foundational puzzle for anyone working in model alignment or synthetic data generation or pre-training. I mean, you observe this truth bias empirically, and you just naturally assume the transformer architecture is somehow filtering reality from fiction.
But we rarely isolate the exact mechanistic reason why that bias emerges in a purely self-supervised setup.
Right. We just rely on the heuristic that truth is simply more frequent. But, as data sets grow, that assumption becomes highly unstable.
Totally. So our mission for this deep dive is to completely dismantle that assumption. We are examining a really fascinating, highly controlled study from March 2026 by Konstantin Krestnikov.
Yeah, titled Truth as a Compression Artifact in Language Model Training.
Right. And we're going to dissect the paper's core thesis today, which introduces this idea of the compression consistency principle. Basically, the model isn't seeking truth at all.
No, not at all. It is strictly seeking the minimum description length, or MDL.
Right. Truth only wins out because organic human errors are incredibly diverse. They're structurally incoherent.
Exactly, which makes them mathematically very difficult to compress within the network's parameters. Krestnikov posits that if a falsehood is systematically coherent, the model's preference for truth completely vanishes.
Which is wild. It's a rigorously controlled test of how error structure, rather than just frequency or scale, dictates a model's factual representations.
Yeah, and since you, our listener, are actively building, training, and fine-tuning these architectures, we're going to bypass the basic definitions today.
Yeah, we're diving straight into the mechanics of cross-entropy, gradient descent, and Kolmogorov complexity. We want to understand what the compressor is doing to the loss landscape under the hood.
So, to really appreciate the paper's results, we first need to formally bridge Shannon's information theory with language modeling.
Okay, let's unpack this.
Right, so at a fundamental level, minimizing cross-entropy loss is functionally equivalent to minimizing code length.
Right.
If we view the training process through the lens of an idealized minimum description length learner, the objective is to minimize the description length of the model itself, so the parameter weights.
Plus the description length of the data given the model, right?
Exactly. The network is essentially just a decompression algorithm.
Okay, let's map this to a concrete heuristic so we can visualize it. Imagine you have to memorize a sequence of 1,000 numbers.
Sure.
If those numbers are generated by rolling a fair die, they're algorithmically random. You literally have to memorize each independent integer.
Right, because the Kolmogorov complexity is massive. The shortest program to output that sequence is literally just a print statement containing the entire sequence.
Exactly. But if those 1,000 numbers are just the Fibonacci sequence, you only need to memorize a very short generating algorithm.
Yeah, the neural network can parameterize that generating function using minimal capacity. It compresses beautifully.
So that's the structural framing for Krestnikov's denoising experiment.
And in this corpus, every single mathematical problem, like expanding polynomials or calculating derivatives, appears exactly twice.
Right, once with the correct derivation and once with an incorrect derivation.
Which isolates the contradiction perfectly. You are feeding the model a one-to-one ratio of truth and falsehood for the exact same prompt, basically forcing the optimizer to choose a path.
So this brings us to the central contrast of the paper, condition J1 versus condition J2. Let's look at the random errors first.
Okay, yeah. In J1, the incorrect answer paired with the truth is just a random error, like a sign is dropped arbitrarily or a constant is just hallucinated midway through an equation.
And when trained on that J1 condition, the models easily extract the correct signal.
Yeah, pair accuracy, meaning how often the model assigns a higher likelihood to the true derivation over the false one. It scales monotonically with model capacity.
Right, so the 3.5 million parameter model hits 65% accuracy, and by 86 million parameters, it reaches 85%.
Because the compressor favors the truth, The random errors lack a shared underlying generating function.
Right? The network would have to spend parameter capacity memorizing each random error individually.
Exactly, whereas the true mathematical rules generalize across the entire data set.
But the dynamic completely shifts in condition J2.
It does. It really does, because here, the false answer isn't a random localized mistake. It follows a consistent alternative rule system.
Right. So, for example, instead of distributing multiplication over addition correctly, the coherent error always applies a false rule, like A times B plus C equals A times B plus C minus 1.
Yeah, it is mathematically wrong, obviously, but it is applied with strict internal consistency across the entire pre-training corpus.
And the result is that the truth bias vanishes entirely.
Completely vanishes. The model cannot distinguish the coherent false system from the truth. Across the varying model sizes, the pair accuracy drops to chance.
Hovering right around 44 to 51%. Right.
Exactly. The alternative rule system can be parameterized just as efficiently as the true mathematical rules. The description length of the data given the model is functionally identical for both paths.
But wait, if I'm looking at the low parameter regime for these coherent errors in J2, there's a glaring anomaly in the data.
Oh, the tiny model.
Yeah. For the 3.5 million parameter model, the accuracy doesn't just rest at a 50-50 coin toss. It actually dips down to 43.5%.
Which is below chance.
Right. It is actively, systematically preferring the incorrect derivation over the true one. If MDL is all about finding the shortest description length, why is it actively favoring the hallucination?
So the author terms this phenomenon textual simplicity asymmetry.
Okay.
Consider the structural impact of the coherent error rule we just discussed. A times B plus C equals
Well,
times B
yeah.
plus C minus 1. Or consider a coherent error in a calculus dataset that systematically drops a complex coefficient during a derivation.
Oh, I see. By taking a mathematical shortcut, the false system's output requires fewer tokens to represent.
Exactly. It is literally textually shorter and syntactically simpler than the rigorous true mathematical derivation.
So the compressor actively prefers the false system because it physically requires fewer bits to encode in the output sequence.
Yes. The cross-entropy objective has zero concept of external correctness. It just blindly follows the gradient toward the most easily compressible signal.
Wow.
And when the coherent error produces a textually simpler output sequence, the model requires less capacity to predict it.
But then as it scales to 86 million parameters...
It gains enough representational capacity to model both the true system and the false system optimally. And that's when the accuracy stabilizes right at 51% pure chance.
Yeah.
Both systems reach an optimal per token loss.
Man. If a single coherent lie completely neutralizes the model's truth compass, that feels incredibly fragile.
It is.
But the real internet isn't one perfectly orchestrated lie. It's an incoherent noise floor of thousands of competing misconceptions.
Right.
So what happens when those coherent errors are forced to compete with each other?
This leads us to the multi-rule experiment. This is where the underlying mechanics of Kolmogorov complexity become really visible.
Here's where it gets really interesting.
Yeah. The researchers introduced a corpus with multiple competing false rules. So they moved from n equals 1, a single false rule, to n equals 2, adding a second competing coherent error.
Now, I would assume adding a second rule just causes like a slight linear degradation in the compressibility of the false cluster?
That's what you'd think, but no, the degradation is not linear. There is a remarkably sharp crossover.
Really?
Yeah. Moving from one false rule to two false rules causes the accuracy to jump dramatically from 47% to 78% on the tiny model.
Oh.
And by the time the dataset incorporates n equals 10 competing false rules, the model's accuracy on the true derivations climbs to 88%.
That completely inverts standard scaling intuition. The model goes from actively preferring the lie to instantly recovering its truth bias, entirely because the alternative rule systems are fractured.
Exactly. And we can trace this directly to the architecture's parameter budget and Kolmogorov complexity.
How so?
Well, when you have one correct rule and one false rule, the complexity of the true cluster is roughly equal to the complexity of the false cluster. Both require minimal parameterization.
Okay, that makes sense.
But the moment you introduce rule A and rule B into the false cluster as a whole is no longer algorithmically simple.
Ah, because to compress the false cluster now, the model must encode a mapping function.
Right.
It has to memorize which specific problem in the data set utilizes rule A and which utilizes rule B.
Yes. And because the assignment of rule A or rule B to a given problem is entirely arbitrary within the corpus, that selector mapping is fundamentally unpredictable.
It's a high entropy signal.
Exactly. The transformer's attention heads attempt to find a predictive feature to route the sequence to the correct rule, but none exists.
So the network is forced to route this through pure memorization in its multi-layer perceptrons.
Right. It must spend roughly log n bits per problem just to encode the selector. And this massive penalty drives up the total description length of the false cluster.
Oh, wow. So the coherent falsehoods suddenly lose their compressibility advantage.
Yeah. The true cluster becomes the path of least resistance, and the model's truth bias is fully restored.
Now, playing the skeptical data scientist for a second, my immediate worry here is cross-entropy token penalties.
Oh, sure.
Whenever I see a jump in negative log likelihood-based metrics that correlates with multiple generated paths, I suspect completion length confounds.
You're thinking the false answers are systematically varying in token count.
Exactly. If they vary as we add more rules, standard NLL is going to penalize them heavily. Did the researchers control for generation length to ensure this isn't just an artifact of the evaluation metric?
They did. They controlled for it very aggressively. They recognized that standard mean negative log likelihood per token can be skewed by generation length.
Good.
So to address this, they implemented a length-matched mean NLL evaluation, strictly controlling for completion length differences between the true and false clusters. The length-matched accuracy remained within 1 percentage point of the standard accuracy across all conditions.
Oh, that's incredibly robust.
Yeah, and furthermore, they cross-verified this using a sum NLL metric, which evaluates the total negative log likelihood over the entire completion. The multi-rule crossover holds up perfectly under both metrics.
So this phase shift is driven purely by the structural complexity of the routing logic, not token counts.
Exactly.
Okay, so the mathematics domain provides a beautifully deterministic sandbox for this, right? Tokens are rigid, dependencies are strict.
Right.
But the pre-training data that you are dealing with every day is continuous and messy. Does this MDL theory hold up against extreme signal-to-noise ratios? And how does it transfer to the continuous embedding space of natural language?
Yeah, let's look at the signal-to-noise bottleneck first. The researchers designed conditions J3 and J4.
Okay.
In J3, the corpus contains a 1:2 ratio. So one correct derivation mixed with 2 random incorrect ones.
Yeah.
And J4 pushes this to a 1:4 ratio.
Wow, okay. And even at a 1:4 noise ratio, the 12 million parameter model manages to extract the true mathematical signal at 65% accuracy.
Yeah, the sheer volume of random errors creates an enormous loss penalty, but it doesn't destroy the underlying compressibility of the true signal.
However, there is a strict capacity-dependent plateau, isn't there?
There is. At the 1:4 ratio, once the architecture reaches the 26 million and 86 million parameter scales, the accuracy completely flattens out around 66%.
So adding more parameters cannot overcome the sheer volume of noise.
No, it can't. The compressibility advantage of the true cluster remains intact, but the model just exhausts its ability to filter the correct generating function from the overwhelming noise floor.
That fundamentally alters how we should view data curation. I mean, you cannot scale your way out of a degraded signal-to-noise ratio, even if the errors are completely random.
Right.
But let's look at how this transfers to natural language. The paper runs a Wikipedia entity substitution experiment to test this on unstructured text.
Yeah. They utilize a named entity recognition pipeline to identify entities in Wikipedia paragraphs, creating 2 distinct corrupted datasets.
Okay.
The first was random substitution swapping Paris for Kumamoto arbitrarily across different articles.
Just random noise.
Exactly. And the second was coherent substitution, a global mapping where every instance of France became Japan and every Paris became Tokyo, preserving strict internal consistency across the entire text corpus.
And the evaluation mirrors the formal math domain perfectly. When evaluated with paired NLL, the random substitution yields a 70 to 71% accuracy.
Meaning the model strongly prefers the true original text.
Right. If an article discusses the Eiffel Tower and the Louvre, swapping Paris for Kumamoto spikes the perplexity because the context vectors in the embedding space sharply disagree.
Yep.
But when the globally coherent substitution is applied, accuracy drops to 46 to 49%.
Because replacing Paris as the capital of France with Tokyo as the capital of Japan remains perfectly internally consistent. The semantic manifold in the embedding space preserves the relative vector distances between the entities. The continuous representations allow the false narrative to remain geometrically contiguous.
So the description length of the coherent alternative world is virtually identical to the real world.
Exactly.
Yep.
And the gradient provides no signal to prefer the factual text.
There is a critical nuance in those numbers, though. The truth bias effect for random errors is noticeably weaker in Wikipedia text, sitting at 71%, compared to the 85% accuracy we saw in the formal math setting.
Yeah, because natural language is inherently softer. It provides vastly more degrees of freedom.
Right.
I mean, a corrupted math equation breaks a rigid dependency chain. The logic just mathematically halts. But a corrupted Wikipedia paragraph can often remain locally fluent, even if it's factually absurd.
So this inherent flexibility in the continuous embedding space actually reduces the compressibility gap between truth and random error in natural text compared to formal logic. So if a coherent false system is fully compressible, and natural language makes falsehoods even easier for the optimizer to swallow, how do we force the model to identify the truth?
Right, that's the big question.
Like, if we connect this to the bigger picture of generating synthetic data, what happens if we explicitly embed mathematical verification steps into the training corpus?
So this leads to the most critical experiment in the paper regarding AI alignment. In Appendix E, Krestnikov explores chain verification.
Oh, this is fascinating.
Yeah, the researchers took the coherent error dataset where accuracy was sitting below chance and chained the reasoning tasks. For instance, the model is required to compute a derivative and then immediately verify that derivation within the same context window using a finite difference calculation.
Right, so if the model utilizes the correct derivative rule, the finite difference check yields a residual of 0. The sequence resolves cleanly.
Yes. But if the model utilizes the coherent false rule, the finite difference check yields an unpredictable, non-zero numerical residual.
Which means the methodology mathematically forces the coherent error to generate a high-entropy, incompressible artifact in the text.
Exactly. And for the tiny 3.5 million parameter model, this structural constraint works exactly as intended.
Oh, wow.
The finite difference residual shatters the compressibility of the coherent error. The model lacks the capacity to memorize the pseudo-random floats generated by the false verification step.
So truth bias is restored.
Yep, it jumps from 43% up to 71%.
As an alignment strategy, that looks incredibly promising. I mean, it suggests we can embed rigorous chain of thought verification into our synthetic data pipelines to mathematically force models to reject coherent hallucinations.
You'd think so.
So what does this all mean? Does it hold as we scale up the parameter count?
No. The paper delivers a scaling paradox that challenges that exact assumption.
Oh, no.
Yeah. As the researchers scaled the models up from 3.5 million to 12 million and then to 86 million parameters, the chain verification accuracy systematically decreased.
Wait, really?
Yeah. It fell from 71% down to 64% and finally dropped to 61% for the largest model.
The higher capacity models actually performed worse at extracting the true rule from the verified data.
Yes, because higher capacity models possess such immense expressivity in their multi-layer perceptrons that they effortlessly memorize the coherent false pattern, along with the specific pseudo-random residual associated with it.
Wow. They internalize the domain's coherent error so efficiently that the weak, incompressible signal of the finite difference residual is simply absorbed into the parameter budget.
Exactly. The gradient penalty from the residual is just not sufficient to force the architecture to shift its core representations back to the true mathematical rule.
Let's connect this mechanistic finding directly to what you, our listeners, are architecting right now. When you are scraping the web or curating pre-training mixtures, diverse organic human errors are relatively benign, right?
Yeah, completely.
A misunderstood concept on a forum or a typo in a technical blog post, it behaves like the random mathematical errors. Gradient descent filters that out because the errors lack a shared generating function and drive up the minimum description length.
The real vulnerability lies in coordinated structured data.
Right.
If a state actor, a bot network, or even an automated synthetic data pipeline generates millions of documents that are internally consistent and systematically cross-reference the same fabricated narratives, they function exactly like the coherent alternative rule system in the mathematics experiment.
They function as a highly compressible alternative reality.
Precisely. To the optimizer, a perfectly structured lie looks identical to the truth. The objective function tracks consistency, not reality.
And the chain verification paradox demonstrates that simply throwing more compute and larger parameter counts at the problem is not a scalable alignment strategy.
No, it's not. Massive scale just gives the model the parameter budget to absorb beautifully constructed lies, verification residuals, and all, without altering its loss landscape.
This requires a fundamental shift in how we evaluate data quality for frontier models. It's no longer sufficient to just filter out incoherent noise.
No, the focus really must shift to algorithmic detection, identifying and dismantling internally consistent alternative rule systems before they are embedded into the pre-training manifold.
Because once the architecture compresses a coherent falsehood, the gradient provides no mathematical mechanism to unlearn it.
Exactly.
So, to briefly synthesize the mechanics we've explored today, the training objective of next token prediction does not inherently optimize for factual truth.
Right.
The truth bias you observe in your models is merely a compression artifact. It emerges strictly because organic falsehoods happen to be structurally incoherent, requiring excessive parameter capacity to encode.
And if a fabricated narrative is mathematically or textually simpler than the truth, the compressor will actively minimize loss by preferring the lie.
Exactly. Now, I want to leave you with a final high-level theoretical question to ponder regarding the limits of this principle. This paper establishes these strict boundaries up to 86 million parameters. But consider phenomena like grokking.
Oh, right.
The sudden nonlinear phase transition from memorization to profound generalization that we observe late in training.
Yeah.
If you are training frontier models at the 100 billion or trillion parameter scale, running for trillions of tokens, does the compressor eventually find a meta-level pattern for reality itself?
That's the dream.
Right. Will the sheer depth of the model's learned representations eventually uncover structural inconsistencies even in highly coordinated disinformation? Or, terrifyingly, does massive parameter scale simply make the architecture exponentially better at compressing and therefore deeply believing perfectly structured lies?
It's a sobering thought.
Gradient descent is a powerful optimization compass, but it has never been pointing toward objective truth. It only points toward the shortest path of description length.
Very true.
Thank you for joining us on this deep dive. We encourage you to test these structural limits within your own architectures and data pipelines. We will see you next time.